So we started studying matching through this example, right? Which after, you may be given different situations, and then ultimately after modeling, what you get is this bipartite graph. So set of vertices A, set of vertices B, and there are cross edges. There are no edges within A, within B, right? So it's a bipartite graph on n cross n or n plus n vertices. And the question is to find the largest subset of edges that are disjoint. They have disjoint endpoints. So that is the question of maximum matching. And there is an easier question of maximal matching. So now what we want to study is when does it happen that a maximal matching is smaller than maximum. So this question will fortunately have a very detailed answer, because of which algorithms are possible to find maximum matching. So if you look at this trivial example where there are 2 plus 2 vertices in the bipartite graph and there are 3 edges, and you start with that 1, 1 edge, then that is a maximal matching, but there is a completely different way to start, which will give you a maximum matching of size 2. Basically, it will give you a perfect matching, right? Because 1 will be matched to 2 and 2 to 1. So how do you get from this bad start to the good start? So the answer will be that what you should do is you should find the following path. If we add what? What edge? No, there is no edge between two. There is no 2 to edge. No, we will not change the graph. Graph is given in the input. No, if you change the graph, then you change your input. You are not allowed that in programming, right? The test case is a hard test case. You are not allowed to change the instructor's test case. So this is the input given to you, but in your algorithm or whatever the analysis you did, in the analysis, if you pick 1, 1 as the start, then it's a bad start. You should have started with 1, 2. Because then you will pick 2, 1 and that will be your maximum matching. So how do you correct your bad start? So the ways you basically find a path in this graph like this. So you find this path 2 to 1, 1 to 1 and 1 to 2, which has the property that the bold edges and the dotted edges, they alternate. Okay, so the maximal matching M that we have found, and the complement of that, which is dotted, you want to find an edge where it alternates. The edges alternate, and where the dotted ones are more. Okay, so you want to find an alternating path with more dots, more M complement than M. So the idea is, if you find such a path, then what can you do? Then you basically, so this is the path 2, 1, 1, 1, 1, 2. From this you just delete 1, 1. And what remains is a maximum matching, or at least a matching which is bigger. Okay, so we'll formalize this this visual idea. So the idea in this picture was what if we consider the alternating path two one 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 two, where 1 1 is in the matching and 1 2 is not, and 2 1 is also not. So consider the alternating path 2 1 1 1 1 2 with m complement edges more, one more than m edges. Okay, so that will be our alternating path, in which what you will do is you will, let's say, do you know the XOR operator? Right, so XOR operator is kind of mod 2 operator, which if you add 2 bits, if they are the same, then the answer is 0. If they are different, then the answer is 1. So it's basically parity or addition mod 2. So in simple words, you just do that. In this alternating path, you XOR with m edges. So when you XOR with m edges, the m edges will get deleted. So now delete the m edges. So let's say the path was called P, then what you are doing is you are defining or you are computing this P symmetric difference M, which is P minus M union M minus P. Okay, in this case it is just deleting the m edge. In general, what you will do is you find an alternating path P, and you only pick those edges which are either only present in P or only present in M. So in this case, for example, you will be left with 2 1 and 1 2. That will be the answer, and that actually grows your matching. Okay, so this is what happened in this example. So in general, this is obviously more complicated. So for that, let us now formally define it. So alternating path in a, so given matching, maximal or whatever, some matching in G, which is XY, right? An alternating path P is such that so remember that it's a bipartite graph. So any path will, if it starts from X, then the adjacent vertex will be in Y, right? And then from Y it has to come back to X. If its length is more than 1, then if it is more than 2, then it has to go back to Y and so on, right? So it alternates within X and Y. But there is another thing which will alternate, which is matching versus non-matching. So the first property has to be well, which is by the bipartite graph that first vertex 1 in P, we assume it to be in X, and the last vertex we assume to be in Y. And both of them are not matched. Okay, so that's the first property it should have, that it originates in X and it ends in Y, where both X and both these vertices, both these endpoints of the path should be unmatched. Unmatched means that there is no edge in M which is incident on first or the last. Okay, so these are unmatched vertices. Like in this example, you had unmatched was what? 2 and 2 was unmatched, right? So this path, that the green path originated in 2 and ended in 2, both were unmatched. So that's the first property. And the second property is edges alternate. Between M complement and M. So obviously, since the first vertex is unmatched, so the first edge will be M complement, and then next will be M, third will be M complement, and so on. In the end, again, you have to end in an unmatched vertex, so that also will be M complement. So this again was true in this example. It started with 2, it took an M complement, then M complement. Okay, so this trivial examples properties gives us this definition of an alternating path in general. Any questions? Yeah, because we have assumed the first property is that both of them are unmatched. So there is no M possibility. If there was an M possibility, then we will not call the vertex unmatched, we will call it matched. So that is a definition here. That is, M is not, no edge in M no M edge incident. Okay, so there is no way to, there is no M edge incident on the first vertex of path P, and the same thing with the last. So all you can do is take an M complement edge. But then second property says that the edges have to alternate, so second edge has to be then M edge. M complement edge, M complement edge, and so on. Okay, so this is a definition. For now, it is just following the trivial example. Okay, there is currently no deeper meaning till I prove a big theorem. Is this clear for now? So what is the big theorem coming up? So the theorem will say that if you incrementally get to a maximal matching, then it can be made bigger if and only if there is an alternating path. So a matching is maximum in the graph G if and only if there is no alternating path. Okay, so if you have incrementally build some matching which can also be a single edge, right? You can just say that I pick some edge and I ask whether this is the maximum or this is one of the maximum matchings. So that will be true if and only if there is no alternating path. If there is an alternating path, then this single edge is not a matching, then you can not maximum, then you can grow it to two edges. Again, you can ask the question whether these two edges they form a maximum matching. If you find an alternating path, then that can be again grown. If you do not find an alternating path, then this is a maximum matching. Okay, so this can be made the base of an algorithm because you have reduced this optimization problem to some path finding problem. Path finding problems are far easier. That again, algorithms you have to see in algorithms course, but this will be the basis. Any questions about the statement? So how do you prove this? Is there an easy side? So what about the forward direction? Can you prove this? So maximum means that no alternating path. Yeah, you prove the contrapositive. So suppose there is an alternating path. Path P in G. What do you do with this? Yeah, so the symbol that was defined before, this P delta M symmetric difference, so using this symmetric difference of the path with the matching M, what do you get? Let's check that. So consider M prime, which is path symmetric difference M, which is, recall we have defined it as P minus M, M minus P. So what is this M prime, right? It's a set of edges. Is this a matching? That's the first question. Are there two edges here which are incident, which have a common endpoint, or are the edges disjoint? So let's focus to see this. Let's focus on the path. So in the path you have so these are the let's say M, and these are the M complements. Right, so suppose the path looks like this. So it starts with M complement, ends with M complement, and in the middle it alternates. So when you do the symmetric difference, what do you get? So the remaining M are here, right? So this is M minus the path. So the things which are not in the path, we don't change them, of course. So those edges will go in M prime, but the M edges in the path, we will remove them. And they will be replaced by M complement edges, right? So 3 will become 4. And you can see that we have not added any overlapping edges, right? Because 2 edges, if they overlap, that will actually contradict property of M being a matching. Is that clear? So this M prime is a matching, is a larger matching. And larger than M. In fact, 1 larger than M. Okay, so which means that M is not maximum. So if there is an alternating path, then M is not maximum. So we have proved that if M is maximum, then there is no alternating path. Is this clear? Okay, so the hard part is the other part. So here again we work with the contrapositive. So suppose M is not maximum. Maximum is needed. Okay, so in that case we need to show, is there a path or not? Which side do you want to show? Yeah, so contrapositive means that you have to show the existence of an alternating path in this case, right? So, so let us assume that let some M prime, let M prime be some matching that is maximum. In the graph that is so now note that from our examples there may be simply no relationship between the maximum matching M prime and the not maximum matching M, right? They can be completely different. So at this point, how do you propose to find an augmenting path? M is a matching which is small, M prime is one which is maximum. The goal is to find an augmenting path. What should you focus on in the graph? So in the graph, there is no point focusing on edges that are outside M union M prime. Okay, so we will actually restrict to a subgraph which only has edges from M and M prime. So let's do that first, because the path, we intend to find a path where the edges will alternate between M prime and M. So we'll just focus on this part of the graph to reduce confusion. So let G prime be the subgraph of G which has edges only from an M prime. Okay, so now what can you say about the properties of the subgraph G prime? If you have just edges of M, you know that the degrees they are all 1. Right now, if you introduce M prime edges also, the degree can be at most what? Degree can be at most 2, right? So now the degrees in G prime, they are either 0, 1 or 2. What can you say about these graphs with degree 2 or less? Exactly. So from your definition of graph days, you recall that then G prime has to be either vertices, I mean isolated for vertices, or paths or cycles. It's a union of that. So G prime, in fact, degree of G prime is less than equal to 2. So G prime has the connected components in G prime, they are of 3 types only, either vertex or path or cycle. Okay, so that is G prime. Now the vertices could be there because, I mean isolated ones could be there because M union M prime may not cover all the vertices, it may not be a vertex cover. Path and cycle are more complicated to explain why they are there. And what we want to show now is that one of these paths is an augmenting path. Okay, we will not care about vertex and cycle components, we will only care about path components, and we will show that one of the path is actually augmenting. That is the proof strategy. So, can you show that any cycle in G prime is even? And with alternating M edges and M prime edges. Do you agree with this? That cycles in this subgraph G prime are even. So well, the easy thing is that in a cycle the edges have to alternate between M and M prime, because if after M edge you again get an M edge, then that will contradict that M is a matching, right? Because no two edges can have a common vertex. So M and M prime alternate in this cycle. Now can it happen that it's odd cycle? How will that happen? So suppose you have this cycle, right? You have an M edge, then you have an M complement edge. So now third edge will also be an M edge, but then you have M and M on M, right? So this is not possible. So which is a pictorial proof for cycles being even in G prime. Is that clear? Okay, so the isolated vertices don't have any edges, cycles are even. So what can you say about the paths? So what you can prove, what this implies is that there exists a path, connected component. There exists a connected component in G prime, which is a path with m prime edges more than m edges. Why is that? Well, because overall G prime has more m prime edges than m edges, right? And all these edges, they will be partitioned into either path or cycles. The cycles m and m prime edges match in parity. So then the pressure is on the path. So one of the path has to have more m prime edges than m edges. Is that clear? So in a path, how many more m prime edges can there be than m edges? It can only be one, right? Because again, the pictorial proof is if this path of length 3 has more m prime edges, then the only way is the following. Right, because you always have this property that m prime and m, they have to alternate. So there are only two configurations out of which this has m prime more than m. So it's always one more. When it is more, it's one more, or it could have been the opposite. But there is currently to be at least one path where m prime is more than m. So does that finish the proof? Yes or no? So we have a path where there are more m prime edges, so it will start with m prime and it will end with m prime, and these edges alternate. So this is an augmenting path. But we were not very careful with one thing. What about edges that are in m and m prime both? We were not careful about those. What about the edges that are common? Sorry? Yeah, basically you go back to the starting point and you can ignore them. You can just think of m prime as being as disjoint from m. The common edges in the subsequent argument, they will not matter. Okay, so you can think of this of these pictures. In fact, I already made the mistake. It's not complement but m prime. But in these pictures, you can just think of m prime as m prime edge being an m complement edge. Okay, that thing works. So the definition of alternating path is satisfied. So this means that this path P is an alternating path. For G comma M, G comma M pair. For that given graph with that given matching, if you assume that the matching is not maximum, then there is an alternating path and we have found it systematically. Right? So this is potentially an algorithm that you can code. It actually finds I mean, if you can find, once you learn in algorithms how to find connected components, then it will find you a path. Okay, so this is completely codable and it's very fast. So this will give you how to go from M to something bigger via an alternating path. Then you can repeat. Okay, but here our goal was to just prove this fact, the other side, and we have that now. So if M is not maximum, then there will be an alternating path. Yeah, so I think here we can stop. You can just take care of M intersection M prime. To complete the proof, you can just think about those edges that are common. And yeah, the remaining proof is the same. Any questions about this theorem or proof? It's something very, very basic, but it has a tricky proof and a huge impact. Okay. So, you can define one more thing, which is complete matching. So complete matching is basically the case where you get the absolutely maximum matching possible. Okay, nothing more is graph theoretically possible. So it basically is the case of if say x and y vertices are of similar size, vertex sets are of similar size, then you can match every vertex of the left hand side. So okay, let's define this. Let M be a matching in the graph x, y, e with, let's say, without loss of generality, the left vertex at x is at most the right one, so y. So in this case, theoretically the maximum matching possible is the one which covers all the x vertices, right? If y is bigger than x, then it will be impossible to cover all the 5 vertices. So maximum you can have is the x vertices. So whichever matching does this is called a complete matching. So M is a complete matching if it includes x or covers x. Okay, and in the case when the sizes of x and y are equal, then we call it a perfect matching. Then this M is a perfect matching. So usually in examples, we are interested in only perfect matchings because the sizes are equal both sides. So what we will do next is we will find necessary and sufficient conditions when will a perfect matching exist? Okay, that's the second major theorem. But before that, let's see an example. So a bipartite graph with degree quite large, let's say greater than 3, and where there is no complete matching. Can you draw such a graph? So you have to find a bipartite graph where the degrees are sufficiently big. So every vertex in X goes to at least 4 vertices of Y. But still there is no way to cover by a matching all the vertices in X. So this is actually a simple construction if you think in terms of complete bipartite graphs. So you take, let's take, so obviously if you look at K d comma d plus 1, in that case you will have a complete matching, right? Because all the d vertices can be matched with the d in Y. But what if you take disjoint union of this with the opposite? So in this graph, is there a complete matching? So for the first copy, D can be matched to D, and in the second copy also D can be matched to D, but still there will be a single vertex which will remain unmatched. Right? So this is actually a good basic example for the case where you can take D to be as big as you want. You can take D to be 100. So the degree of the bipartite graph will be 100. In fact, vertices are also equal in number. So you have 201 on both sides. But every matching will miss at least one vertex on the left and hence on the right. Is that clear? So there are these examples for all D. Any questions? Okay, so you have to think about the reason why this happened. Why was there no complete matching available in this graph? And the reason for that is basically that when you look at a subset of D vertices, there is a subset of D vertices which doesn't have that many neighbors. Do you agree with that? There is a subset of vertices where let's draw this further. This is X, this is Y. All the connections are here, and all the connections are here. Can you give me a subset of vertices which is of size, let's say S, but their neighbors are of size less than S in this graph. Well, 1 and 2 clearly have many neighbors, 4, 5, 6 also, and their subsets also have enough neighbors. But if you look at 4, 5, 6, then the problem is that the neighbors of 4, 5, 6 are only 2. Right? So for any proper subset of 4, 5, 6, there are enough neighbors, but if you look at 4, 5, 6 whole, then there are, for 3, there are only 2. So 4, 5, 6 has only 2 neighbors. So which means that a matching will not be able to cover all the vertices of X, because if it did, then 4, 5, 6 should have had 3 neighbors. Is that clear? So this is the property that we will now mine. So the simple property that, so let us first define the neighborhood of a subset. For subset S of X, define its neighborhood N of S as those vertices in Y such that there exists a vertex in S which is a neighbor. Okay, so it is basically, in simple terms, it is just saying that what are the neighbors of all the vertices which are present in S, union of that. So that is called the neighborhood of a subset or a set of vertices. And the property of complete matching is the following, that if there is a complete matching in G, then it means that the neighborhood size is at least S. Okay, and the contrapositive basically says that if you find an instance where the neighborhood is smaller than S, then it is certifying that there is no complete matching in the graph. And this is true, by the way, for all subsets. Right, so this is the property that for all subsets, neighborhood is at least the set itself. Now, what can you say about the converse of this statement? Do you have an example where all the subsets, if you go through them, their neighbors are big enough, their neighbors are many, but yet there is no complete matching? So this is called Hall's condition. And Hall proved that actually this is if and only if. So it's called Hall's marriage theorem. It doesn't refer to Hall's marriage himself, but just that you can model questions of preferences in marriage also as this bipartite graph. So what he showed is complete matching in G if and only if for all subsets the neighborhood is large. Okay, neighborhood is at least as big as the set itself. Is the statement clear? So how will you prove this? How will you show that if this is true for all subsets, and remember that these conditions are way too many. For n vertices in X, there are 2 raised to n of these conditions, right? Because the subsets are 2 raised to n many. So this is a very large number of inequalities, and from this you want to deduce that there will be a matching which is maximum, and also it completely covers X. How do you show this? So here we will, so this is the second major theorem. We'll use here in the proof the first major theorem, which is augmenting path existence. Okay, so we'll show that, okay, there are again 2 directions. The easy one is the forward one, right? Because you look at the contrapositive. If there exists an S such that the neighborhood is small, then it means that there is no complete matching. So that's the easy part. The hard part is what we are now talking about, where you have to assume that for all S, neighborhood is large, and let, in this case, consider a maximum matching M that is not complete. Okay, so suppose, so if possible, pick this incomplete maximum matching, and we are also assuming that Hall's condition is true. So what we want to do here is get to a contradiction, right? So if we deduce a contradiction from in this setting, then it means that every maximum matching is complete. There is no incomplete maximum matching. So the goal will be then to show that with this M, there is an augmenting path, right? Because if there is an augmenting path, then M cannot be maximum. That will be a contradiction to the previous theorem. So that's the idea. Show that there exists an augmenting path for this graph and for this matching G comma M. Okay, so yeah, this will also require a new trick. So it's best described in a picture. So you have X here and you have Y, which is possibly larger but not smaller than X. So let us pick an unmatched vertex X0 here. So let X0 in X be unmatched. When I say unmatched, again, obviously I mean that no edge in M is incident on X0. not incident on x0. Okay, so pick such a vertex and yeah, what do you do with this? Do you have any promise that there is a neighbor of x0? Yeah, you have the promise, that is Hall's condition, right? So whenever we are with a vertex which seems lonely, there will be a neighbor given by Hall's condition, right? So Hall's condition says that this x0 cannot be alone. So there is an edge. Which will give you, let's say, y1. And since we have assumed that x0 is an unmatched vertex, this edge can only be an M complement. Right? So by Hall's condition and by the assumption of x0, you get this picture. There exists y1 in the neighborhood of x0 which is unmatched also. This is what will basically, you repeat this idea and you will get the proof. You just have to repeat this. So how do you repeat now? Now you look at y1, it is unmatched. I want to deduce that I can come back to x from y1. So think of this as a path in direction. So from x0 I went to y1. Now to make progress I want to come back to big X, because anyways in big Y I cannot go anywhere, there are no edges. Right? So to move forward, to get this augmenting path, I have to come back to big X. How do you come back to big X? What is the promise that there will be an edge or a neighbor? Hall's condition we seem to have exhausted. Exactly. So here you use the assumption that x0, y1 both are unmatched. If they are unmatched, then so basically they are unmatched and you are unable to include this edge to grow your matching M. Right? Why is that? What forbids you from adding this and growing M? What forbids is that this is already incident on some M edge. So there is already an M edge, a bold edge, which is taking you to some x2. Right? Because if this M edge did not exist, then you could have just happily added the M complement edge inside M and gotten a bigger matching. Wait, I made a mistake before, I guess. Yeah, I should not have said unmatched. That we did not deduce. Yeah, all Hall's condition gives is that y1 is in the neighborhood of x0. It doesn't say anything about its matching or unmatching. So here you ask the question whether it can be matched or unmatched. So if it is, then we grow M, which is a contradiction. Right? So then, which means that y1 is actually matched. So since it is matched, the matching will take you to x2 now. What next? So again, you use Hall's condition, and x0, x2 is now a doubleton instead of a singleton. So it has a neighborhood of at least 2 elements, and that will take you to y3. So again, by Hall's condition, I should not draw this edge actually, this is not deduced yet. So Hall's condition only tells me that there exists a y3 in the neighborhood of x0, x2, which is different from y1 of course, but it doesn't tell you whether y3 is connected to x2 or connected to x0. So that will give you two possibilities, right? How do you handle these possibilities? Case 1 is that x2, y3 is an edge. Can it happen? Or what happens if it happens? So if that is an edge, then it can only be an M complement edge. It cannot be an M edge. And so what? So it's an augmenting path. Can be connected to what? Like what? No, so the case is x2, y3 is an edge. That's case 1. So this is an augmenting path then, right? Because x2, y3 edge can only be an M complement edge. So this means that x0, y1, x2, y3 is an augmenting path. So which is again a contradiction. And what is case 2? Case 2 is that y3 with x0 is an edge. So then what happens? Well, so with x0 there can only be an M complement edge. So in that case, there is an M complement edge between x0 and y3. What does that mean? Sorry? So what do you do in this case? If this happens, that is case 2. Well, that's an augmenting path again, because from y3 to x0 to y1 to x2, this is an augmenting path, right? So y3 x0, sorry, made a mistake, no. Yeah, that's not an augmenting path, so this has to be dealt with. I guess y3, we can say that again x0, y3 itself is an augmenting path. Yes, but in augmenting path you only need start end to be, you need to show that y3 is unmatched. So why is y3? Yeah, I see. So then if there is a matching, you move forward. You don't stop here. If there is an M edge going out, then you will just go to x4. So basically, if there is a way to come back by an M edge to x, then you will take that path and you will keep drawing this picture, or there will be a point where you cannot come back by an M edge. And then you have to argue that there is an augmenting path. So in case 2, if you assume that there is no moving backward by M edge, then there will be an augmenting path. It implies an augmenting path. Which implies a contradiction. Or in case 3, x4 exists, y3, x4 is in the matching. So in this case, you just proceed with the path. And ultimately, you will get a contradiction, like case 1 or case 2. Is that clear? Because, it's a finite graph, so at some point you will reach a stage where you cannot go further, or you cannot go back to big X. So then you will be forced to use some other already seen xi, and at that point you have an augmenting path. So all the contradictions in the end are like case 1, case 2. Case 3 only extends the length of the augmenting path. So this contradiction means that in all cases you have a contradiction, so it means that M has to be, that M is already complete. Is that clear? Okay, so that pretty much finishes important properties in graphs. Maybe we'll give few minutes tomorrow, but for now we stop.